Okay.
Hi, students. Let's wrap up lesson 14. This is video F. It's just a quick review. Might be my shortest video ever. Who knows what kind of tangents I get on. But here, let's wrap up 14. The rest of the course, we're moving on to what's called statistical inference, which basically means take a sample of the population, use that sample to make decisions about the whole population. We need chapter 14. That's the theoretical framework for statistical inference. What is statistical inference? It's creating confidence intervals. This might be brand new to most students, unless it's come up in class or something, but we're creating confidence intervals and we'll be running hypothesis tests. Starting in lesson 15, this is the rest of the course. Okay? The next three lessons, 15, 16, and 17, we're going to focus solely on categorical variables, and we learned all the theory for that in lesson 14. So in the next three lessons, everything is categorical. So Kim Shepard in the previous video, the question was gun ownership. Yes or no? Does your household own guns? It's categorical. All right. How do we summarize categorical variables? With proportions. So when working with this type of variable, we'll be using sample proportions. Keep this framework in mind for probably the next 2 or 3 weeks in class, because that's what we'll be focusing on. All right. Flip the slide, get this cleaned up. To perform statistical inference, hypothesis tests, and confidence intervals, there's always going to be a theoretical model sort of lingering in the background. That's what we've been talking about in this lesson. That normal model for p hat. All right, so the sample proportion, when certain conditions are met, closely will follow what kind of model. I just said it, it's a normal model. When we're working with normal models, I need the values of two parameters. One's the mean, the other is the standard deviation. So this is review. This isn't the first time you're seeing this, but the mean of the theoretical model, the symbol is mu with a subscript p hats, and that mean is just equal to p. In all of the problems in chapter 14, lesson 14, we've always said, presume that we know the true proportion. Like, presume in Cecil County that 45% own guns, just like nationwide. Do you think moving forward we'll know this? Like, honestly, do we know the proportion of Cecil County homes that have guns? We won't know it. All that inference that we're going to be doing is going to be focused on what's the true value of P. Okay, so that's where we're going. That's the mean. We do need to get the standard deviation. So sigma of p hat, standard deviation of p hat equals, it's the big square root thing, p times 1 minus p all over n. So a little computation to do, but that's pretty easy at this point. We've done a few of them. All right. Really need to emphasize the conditions. For that normal model to take effect, for us to be able to effectively model p hat with a normal model, I need to check those conditions. There's 4 of them. Number 1, always stay focused. What kind of variable do I have? It's got to be categorical. Number 2, what kind of sample do I have? We hope a simple random sample, but practically speaking, that's really impossible. So we'll settle for an unbiased sample. Think back to the Mother Jones gun ownership example. If I was going to sample homes in the county, I would need to sample homes from the urban areas, the rural areas, northwest, southeast, everywhere, right? Get a good representative sample. I wouldn't focus just, say, on, I don't know, Rising Sun exclusively. That'd be biased towards Rising Sun and not the whole county. Okay. Part 3, the sample size should be smaller than 10% of the population size. So number 3, sample size less than 10% of population size. We check this to make sure, it seems a little silly, but to make sure our sample isn't too big. If the sample's too big, you might run into problems with independence. To me personally, I can never have enough data, but we still check this just to make sure that we're proceeding with all the conditions met. So sample size less than 10% of population size. And then finally, for that categorical variable, I need to expect at least 10 successes and 10 failures. So expect 10 successes, 10 failures. If we're going to arbitrarily label a success as a house has a gun, I don't know if that's a success or a failure, it probably depends on your worldview, but I need at least to expect 10 homes with guns and 10 homes without guns, right? It's arbitrary which one I call success and failure. All right, we've always got to check those. If you flip the page, I don't think there's any blanks to fill in, but don't turn that video off. I'll give you some pearls of wisdom here. So let's think about where we're going. Just take a minute. The first bullet point. Typically how this works, we're going to determine that theoretical model first for the statistic of interest. You know, it's p hat for the next 3 lessons, based on certain assumptions about our population of interest. So what do I mean by this? The model may or may not be correct based on the quality of the assumptions. All right? So, well, I might start by assuming in Cecil County that 45% of all the homes are gun ownerships, because that's the published figure I found in Mother Jones magazine. And I'll cook up that model based on that assumption. That assumption may or may not be correct. The proportion of gun ownership in Cecil County may be vastly different than 45%. And when we move on in this course, let's go collect that data. Let's see what the data tells us and make a statistical decision. It's our job to collect the data, weigh the data against that model. We start with that theoretical model, collect the data, weigh the data against that. The data might convince us that the theoretical model is faulty, and that might lead us to change our minds about the population. It's interesting stuff. It's like you come up with a theory and then collect the data to test the theory. Other times, maybe our hunch was wrong. Maybe, I think more than 45% of homes in Cecil County own guns. I don't know, I think that. Maybe my hunch is wrong. I collect my data and the data doesn't convince me. Right? The data won't convince us that our theoretical model is faulty. That's that normal model that we cooked up at the beginning. In these cases, we'll probably just continue to go along with our original assumptions. Right? The data didn't persuade us to change our minds. Recall the Cecil College smoking example. So we open the unit with this one. We began our investigation. We assumed that 20% of the students here were smokers. And the 20% came from the national figure because 20% of people are smokers. We cooked up a normal model based on that 20%. Now we can go collect data to try to refute it if we think it's more than 20%. Once we collect our data, let's think of the whole process. We determine just how unusual it would be to obtain our data. And remember, in this unit, we're going to summarize our data, right, by calculating a p hat. So collect some data at Cecil College, determine the number of smokers, convert that to a proportion, a sample p hat. Now I look, is that p hat way out in the tails? Is it towards the center? And so let me read this whole thing. Once we collected our data, we determined just how unusual it would be to obtain our data if that normal model we cooked up was a reasonable normal model. Okay? We're weighing the data against our original assumptions. Then what do you do in statistics? You make a conclusion about the whole school, the entire population, just based on our small sample. In a nutshell, this is the definition of statistical inference. I want to know about the entire Cecil College, but I'm not going to collect data from 2,500 students. 200 maybe. Based on the 200, make a decision. When the collected sample proportion falls far out in the tails, that's unusual. If the data is unusual, then the data have convinced us to change our minds about the whole population. That initial assumption no longer good. We're going to change our minds and make a new conclusion. Okay? Let me flip this. Far in the tails, a little bit arbitrary. But we know normal models. We know probabilities. We know z-scores. It's all based on that stuff we've been working all semester. Far in the tails really depends on the exact normal model we're using. And I like the way that I think here. We have to recall our abilities to work with z-scores and to shade under normal models to switch over to probabilities. All these problems turn into probability problems. And the question in quotes, what's the probability that I just drew my sample or one even stranger? Further out in the tails. Like start at yours and then shade out. If that model is good. When you're far out in the tails, that's unusual. That'll lead us to change our minds. If you're not far out in the tails, it's not unusual. And we'll probably just continue with our original assumption. All right, so this feels like the last slide. The rest of Math 127 is really based on these ideas that we learned in Lesson 14. Okay, so you've got resources. Make sure you ask us as your instructors. And really try to understand the material, because I think it'll help you appreciate what we're going to do with confidence intervals and hypothesis tests. So thanks for watching, and we'll see you in class